Welcome to the video lecture on the zeros of a polynomial. In this video lecture, we're going to talk about how to find the zeros or roots of a polynomial using the calculator as a guide, but trying to find these zeros as algebraically as we can. So we're going to start off by using a theorem which says that a polynomial function of degree n, where n is greater than or equal to 1, has at most n real zeros. We count each zero as many times as its multiplicity. So if it repeats, we count it for as many times as it repeats. Now if you take a look at this example, we have p of x is this cubic polynomial. And because it's degree 3, because it's cubic, that means that we are going to have at most 3 real zeros. Now there could be fewer than this if some of these zeros happen to be complex numbers instead of real numbers. But you could have at most 3 real zeros, the same as the degree. Now this particular cubic happens to factor, and it would be hard probably to guess that this is how it would factor, but if you were to FOIL this out and verify it, you'll see that you'd get back the original cubic. And the 3 factors of this cubic are x minus 3, x minus 2, and x plus 4. And so what we would know if we were able to get this factorization is that our 3 zeros would be 3 from this first factor, 2 from the second factor, and a negative 4 from the third factor. Now what I want you to notice here is what happens if you were to multiply 3 times 2 times 4. I'm going to ignore the sign for a moment. 3 times 2 is 6. 6 times 4 is 24, and lo and behold, that 24 is exactly the same as the constant term on the end of our polynomial. So there's a theorem that we're going to talk about in just a moment that says the zeros that you get for your polynomial have a relationship to the constant term and also some other coefficients of your polynomial as well. So this is a theorem that's going to give us a list of possible rational zeros for a polynomial function if the coefficients are integers. So you have to be starting off with a polynomial that has integer coefficients, okay, no fractions, no decimals, nothing like that, just nice integers. And what the rational zeros theorem says is that if you have this polynomial with integer coefficients, then every rational zero of the polynomial has to be of the form p over q, where p is a factor of a sub 0, which is our constant term on the end, and q is a factor of a sub n, which is our leading coefficient. Now remember, this is going to find us the rational zeros. Rational zeros are going to be the zeros that are fractions or decimals, or can be written as fractions or decimals, that don't that either terminate or repeat. So remember, rational number means anything that can be written as a fraction, or if you're thinking about decimals, any decimal that terminates, which means stops, or has a pattern to it and repeats. So this is not going to find us zeros that would be irrational, like pi or square root of 2 or something like that, and it's not going to find us any zeros that would be complex. But it is a pretty nice theorem to use to help sort of narrow down the possible rational zeros that might exist. So let's see how this theorem works in action. So here's a cubic polynomial, 2x cubed plus x squared minus 13x plus 6, and we want to find all of the real zeros. Now before we jump into that, we're going to use this rational zero theorem to make a list of all the potential rational zeros that exist for this polynomial. So what we're going to do is find our factors p and q. And you have to remember that p is the factor of the constant term, so that would be this constant 6 on the end. So what does it mean to be a factor? It means you have to be a number that divides evenly into 6, and this includes both possible signs, positives and negatives. So we want to make a list of all the factors of 6, all the numbers that divide evenly into 6. So that could be 1, that could be 2, that could be 3, or that could be 6. And I'm going to put plus or minus signs in front of all of these so that we include both possibilities. So the factors of 6, 1, 2, 3, and 6. Now Q is going to be the factors of the leading coefficient. So if our cubic term has a coefficient of 2, then we want factors of 2. So what numbers divide evenly into 2? Either 1 or 2. And again, I'm using plus or minus signs in front. So that means, according to this rational zeros theorem, our possible rational zeros would have to be of the form p, where p is one of these numbers up here, divided by q, which is one of these numbers down here. So we need to make a list of all of those possibilities. So I'm going to take each of the p's and divide them by each of the q's. So let's start with 1. This could be either 1 over 1, which is 1, or 1 over 2, which is a half. And because both signs are possibilities, I'm just going to put a big fat plus or minus sign out front, and that's going to be the case for all of these. So all of my potential zeros here are positives or negatives. So we did the p using 1. Now let's use p being 2. So we could either have 2 over 1 or 2 over 2. Well, 2 over 1 is 2. 2 over 2 is 1, and I've already got that in my list, so I don't need to include it again. Now let's move to the next p, which would be 3. So either 3 divided by 1, which would be 3, or 3 divided by 2, which would be 3 halves. And then if I go to the last p-value 6, 6 divided by 1 is 6, 6 divided by 2 is 3, and I already have that in my list. Now what do these p over q's represent again? These are the potential rational zeros of this cubic polynomial p of x. Potential, okay? So that doesn't guarantee that they actually are zeros. It just means if there are any rational zeros, it has to be one of these choices. So we still need to check to see which ones of these actually work. Okay? So how do you check? Well, first you have to make a guess. You have to go through this list and say, okay, which one do I want to assume is a real zero? And then we're going to check it out using synthetic division, a nice, simple, quick method for dividing a cubic polynomial by a linear factor. So for example, say we wanted to try 1, the first number in our list here. Then what I would do is I would use synthetic division. So synthetic division uses the coefficients of our original function here and just list them across the top. Make sure you're going in descending order and make sure that you have used every possible term. If there's any powers that are missing, you need to have a coefficient of 0 to hold its spot. So my coefficients are 2 for the cubic, 1 for the x squared, negative 13 for the x, and 6 for the constant. And I'm going to try and see if 1 is a 0. So that means I'm going to put 1 in my little box in the corner, and I'm going to draw my line, and I bring down the 2, and then I'm going to multiply. 1 times 2 is 2, add down, 1 plus 2 is 3, 3 times 1 is 3, add down, negative 13 plus 3 is negative 10, multiply, and I get negative 10, 6 minus 10 is negative 4. Now how do I know if it works? Well, if 1 really was a 0, then what should my remainder be? It should be a 0, and this is not a 0 remainder. So that means it doesn't work. So 1 is not a 0 of this polynomial. Okay, so that one didn't work, so we need to take another guess. And I'm going to show you in a little bit some strategies for how to make some good guesses. But on this one, let's just take a random guess here, and let's try, say, 2. Okay, so I'm going to jump around in my list here. I want to try to avoid the fractions if I can because they get a little messy to handle. So I'm just going to try the next integer value here, 2. And again, I'm just going to do my synthetic division again. So that would be 2, 1, negative 13, and 6. Again, the same coefficients of the original polynomial that I had. And this time I'm going to put 2 in the box, and I'm going to repeat this process again. So if I bring down the 2, 2 times 2 is 4, 1 plus 4 is 5, 2 times 5 is 10, negative 13 plus 10 is negative 3, 2 times negative 3 is negative 6, 6 minus 6 is 0. And that means that 2 is a 0 of my polynomial. Now you can do this many ways from this point on. You can then go through your list again and try to guess another potential 0 from this list, like 3 or 3/2 or 1/2 or 6, or even the negatives as well. Or you can use something that the synthetic division tells you, and that is this quotient down here. Remember these coefficients down here that we got below the line? Those are the coefficients of the quotient. And remember, the quotient is 1 degree less than what you started with. So if this was a cubic to begin with, and I am dividing by really the factor x minus 2, then what I would be left with should be 1 degree less than a cubic, in other words, a square or a quadratic. So this should be 2x squared plus 5x minus 3, and that's your quotient. And that means that so far, this polynomial has as a factor, since 2 worked, x minus 2 must be one of the factors, and this quotient as well is left over. And if I were to FOIL this all back out again, I would get back this original polynomial. Now, if you're left with a quadratic quotient, like we are in this problem, that's usually good news for us, because we know how to solve quadratic equations in many different ways. If we're lucky, it'll factor further. If we're not so lucky, then we might have to jump in and use the quadratic formula. And in the video lecture today, we're going to use both of those techniques. But on this particular example, we get a little bit lucky because this trinomial right here will factor further. So let's see how it factors. I'm going to set up my 2 sets of parentheses. I need a 2x and an x to get that 2x squared, and I need a 1 and a 3 to get that 3. If I put the 1 here and the 3 here, that'll give me a 6x and a 1x. If I make the 6x plus and the 1x minus, then I'll get a positive 5x, but I'll also get a minus 3 on the end, which is what I want. So that means for my zeros, I'm getting this 2 that we already knew about from our synthetic division, but I'm also getting 1/2, which happens to be in my list up here, and I'm also getting negative 3, which also happens to be in my list. So we could have just tried guessing and checking everything in this list, but that takes a lot of time. If you're not a very good guesser, then it could get pretty tedious. So what I usually do on these problems is I try to get a little bit lucky and find at least 1 0 through synthetic division, and try to get my quotient down to a quadratic. And then once I know that I've got a quadratic, I can either factor it, like I did on this problem, to find the other 2 zeros, or I might have to resort to quadratic equation to find those other 2 zeros. And in this example, we had 3 zeros, and they were all rational because they were all either integers or fractions. Okay? All right, let's try another example. So we're going to list, first, we're going to list the possible rational zeros for this 4th degree polynomial, and then we're going to find all of our zeros, find all the real zeros. So to use that rational zeros theorem again, you're going to list your p's and your q's. The p's come from the factors of the constant term, which in this case is that 10. So we need to list all the possible numbers that divide into 10 evenly. And I'm going to use pluses and minuses. So obviously that would be plus or minus 1, or plus or minus 10. 1 and 10 make 10, or plus or minus 2, and plus or minus 5. 2 and 5 make 10. So those are all the factors of 10. Then your q's are your factors of your leading coefficient, which in this case is just an implied 1. So the only divisors of 1 would be 1 itself. So that makes our list of p divided by q's fairly simple to do. We're just going to take each of these p's and divide them by 1, which is going to keep them the same. So we're going to get back plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Now this one has several possible potential rational zeros, and you could go through each potential value here and try synthetic division on them. Here's a nice hint that I like to do, or a nice little strategy that I like to do, and that is to use my graphing calculator to help me get a good guess. Now you can't on these problems. I'm not going to allow you to use your graphing calculator to find those zeros and use that zero command. Instead, I want to see it done algebraically. However, you can use your graphing calculator to at least give you a place to start off from, a good jumping off point so that you're making a good guess and going from there. So here's what we would do. We would go to our y equals, and we're going to type in this 4th degree polynomial. So x to the 4th minus 5x to the 3rd minus 5x squared plus 23x plus 10. Whoops. Make sure I have it typed in right. So x to the 4th minus 5x cubed minus 5x squared plus 23x plus a 10. And initially here I'm just going to do that standard window. And we're not really going to waste a whole lot of time here on getting a good window so we can see that graph. All I'm interested in this problem are zeros, and that's something we can just see from this window right here. You see a 0 over here on the left, you see 1 here close to the origin, you see another one over here to the right, and then 1 all the way on the right over here as well. And remember, our standard window, these are going by 1s across that x-axis. So what we're looking for here are what would a good guess be for the zeros that are in this list here. So we're looking for nice integer values that we can see from our graph that are probably going to be zeros for this polynomial. So for example, the one on the left here looks like it's hitting right at -2. So I might guess -2 as a potential zero. The second 0 here is hard to tell because it's not landing right on one of those tick marks. So that's one that I probably couldn't guess, so I'm going to jump over that one. The third 0 as well does not land directly on a tick mark, so that one is probably a fraction of some sort, so I'm going to ignore that one for now. And then this one over here on the right is at 5. It looks like it's at 5. So out of those 4 zeros that I am seeing, it looks like the two nice ones would be -2 and +5. And those are in my list of p's over q's. So what we're going to do is perform our synthetic division using -2 as a guess and using +5 as a guess. And then we'll go from there. So you have to use synthetic division to actually check. But you can use the calculator to help you find a good guess. Okay, a number to start off with that's in your list of p's over q's. So let's go ahead and try our synthetic division. My coefficients of this 4th degree polynomial are 1, -5, -5, 23, and 10. And we said that -2 looks like it's a 0 on my graph. So I am going to do synthetic division using -2, and I'm going to hope that I get a 0 remainder. So I bring down the 1, get -2, this is -7, I get 14, 14 minus 5 is 9, -2 times 9 is -18, 5, -10, and yes, I did get a 0. So one of my zeros is going to be -2. Now, here's a nice little trick that you can do here. Instead of starting your synthetic division from scratch and using these coefficients of the fourth degree all over again, we're going to use the quotient that we left off with. Remember that we thought 5 was a potential 0. So if 5 divides into this polynomial, then it also has to divide into this quotient as well, since all we've taken out from this quotient is the factor x plus 2. So if x minus 5 is a factor, then it's got to be a factor of this sort of remaining coefficients. So what we're going to do is perform synthetic division right where we left off. So I'm going to put 5 in my little box, draw my line, and I'm going to now use these coefficients of the quotient as my new starting off point. So I bring down the 1, 5 times 1 is 5, negative 7 plus 5 is negative 2, 5 times negative 2 is negative 10, 9 minus 10 is negative 1, 5 times negative 1 is negative 5, and there's that 0. So we also have proven now that 5 is a 0 as well. So at this point, the other two zeros that we see over here are at fractions, and I don't even have any fractions in my list of p over q's. So that probably implies that they are not going to be nice fractions, and that they are either irrational, or that they must be irrational numbers if they're not in my list of rational zeros. They're not complex, because if they were complex zeros, I wouldn't even see them on my graph at all, because when we graph a polynomial, we're only graphing real numbers. So the fact that I can see them means the other two zeros must be irrational. And the only way I'm going to find those is by using the quotient that we had left right here and somehow solving that algebraically. Now remember, we performed synthetic division twice. We started with the fourth degree. After the first time through, this quotient right here would have been a third degree quotient. So then when I perform synthetic division again, the degree goes down one more, so that means this quotient down here must be a second degree, which is good, because now that means this is a quadratic equation, and it would be x squared minus a 2x minus a 1. And as long as you have a quadratic, you can always solve it algebraically. So how do we solve this thing? We're trying to find its zeros. It doesn't factor because the signs don't work. If we had a plus 1 here on the end, then we would have been able to factor it. But with that minus 1, no such luck. So what we're going to have to do is use quadratic formula. So let's go ahead and apply the quadratic formula. That's going to be x equals minus b. So here's my b. So minus that would be positive 2 plus or minus the square root of b squared, so negative 2 quantity squared becomes 4, minus 4 times a, which is 1, times c, which is negative 1, all over 2 times a, 2 times 1. So let's simplify. We get 2 plus or minus, we're going to get a 2 in the bottom, and under that radical we're going to get a 4, and a minus become a plus 4. So this is 2 plus or minus square root of 8 all over 2. And I would ask that you reduce that radical. Square root of 8 is square root of 4 times square root of 2, or 2 root 2. So this is 2 plus or minus 2 root 2 all over 2. And then I would ask that you reduce that as well, because all of these outer numbers are divisible by 2. We can't touch the 2 under the radical, because it's under a square root. We're only looking at the outside coefficients. So let's divide all three of these outer numbers by 2, and that's just going to leave me with 1 plus or minus 1 square root of 2, or just root 2, and I don't need to write a 1 in the bottom. So that means my other two zeros are right here. 1 plus root 2 and 1 minus root 2. And just a little note here. Those are irrational because they involve a square root of 2. So these would be decimals that never terminate and don't repeat at all. So they're not nice rational numbers in our list. And notice also that they are what we call conjugates. So they both look identical except that the sign in between them is opposites. And that's always the case when you're dealing with irrational zeros. They always come in conjugate pairs. Can't have one without the other. And this is also true for complex solutions as well, and we'll see that in some later examples. So anytime you have irrational zeros, they will come in conjugate pairs. They'll come in pairs, and the same with complex zeros as well. They'll come in conjugates. Okay, we'll practice this some more, but before we do that, let's talk about something called the boundedness theorem. So this theorem says that if you have a polynomial with real coefficients, if we divide p of x by x minus b using synthetic division, and if the row that contains the quotients and the remainder has no negative entry, then b is an upper bound for the real roots of that polynomial. So this is a way of determining not necessarily the exact zero, but it's a way of determining sort of an upper bound, and as we'll see in number 2 here, a lower bound for what that where that real zero has to be. So it's a way of sort of narrowing down the location of a zero if you can't find it exactly. So we're going to be able to find an upper bound if that quotient row using synthetic division is no negatives. So in other words, they're all positives or zeros. If we divide and do synthetic division using x minus b, and we end up with that quotient row having entries that are either non-positive and non-negative, and they alternate, so they're alternately non-positive and non-negative, then we say that this b is a lower bound for the real roots. So what does non-positive mean? It means you're either 0 or you're negative, and non-negative means you're either 0 or you're positive. So the entries in that quotient row would have to alternate between pluses and minuses, plus, minus, and so forth, also allowing 0 as a potential value in that quotient row as well. So let me show you what I mean by how this is going to work. So we're going to show that -3 and 5 are the lower and upper bounds for the real roots of this 4th degree polynomial. So what we're going to do is we're going to do synthetic division using -3 in the little box and 5 in the little box. So here's my coefficients of my 4th degree polynomial. I've got coefficient of 1 for that 4th degree, a -2 for the cubic, -9 for the x squared, 2 for the x, and 8 for the constant. And we're going to divide by -3 in that little box. So if I bring down the 1, I get 1. Multiplying gives me -3. Then I add to get a -5. This gives me 15. 15 minus 9 is 6. Multiplying gives me -18. Adding down is -16. 16 times 3 is 48. And 8 and 48 is 56. So notice the signs on this thing. It's plus, then minus, then plus, then minus, then plus. That's what I mean by it has to alternate between non-positive and non-negative in this quotient row. So if it does that, then that means the number in this little box, this b right here, is a lower bound. So -3 is a lower bound. And I'll explain more about what that means in just a moment. Let's check out what happens with 5. So we're going to start from scratch again. We're going to put those coefficients of our 4th degree across the top, and this time we're going to put 5 in that little box. If I bring down the 1, I get 1. Multiplying gives me 5. 5 minus 2 is 3. 15 gives me a 6. 30, 32, and 32 times 5 is 160. So when I add down, I get 168. So if you look at all of these, they're all plus. And that's what this number 1 says. If the row that contains the quotients and the remainder has no negative entries, so either positives or zeros, then we say that that b, or that number in the box, is an upper bound for the real roots. So +5 is an upper bound. Now we've done a few examples here of finding zeros, and they turned out to be fairly nice, either nice integers or something that we could solve algebraically. But sometimes it's going to be impossible to find the actual zeros algebraically. So what we've just come up with here, what our conclusion is that the zeros of this fourth degree polynomial, we don't know exactly what they are, but we know that all of the zeros of this fourth degree must lie between -3, oops, sorry about that. They must lie between -3 and +5, and I'm going to write it as an interval. So all the zeros of this fourth degree, even though I might not be able to find them exactly, I know that they all are between -3 and 5. So they all have to hit the x-axis somewhere between -3 and 5. And I know it doesn't hit exactly at -3 or +5 because I didn't get a zero remainder. So I know those two aren't actually roots. So all the zeros must be somewhere in between. So that's why I used parentheses. So this boundedness theorem just gives you a way of sort of narrowing down the range for where your zeros have to lie. Okay, let's try some more examples. So we're going to find the exact value of all zeros. Now if you see that phrase, exact value, that means you're not allowed to use your calculator, because the calculator is going to be giving you approximations when you use that zero command that's under calc. So we want to be able to try and find these zeros exactly, which means trying to do it algebraically, solving something, or using synthetic division. Now the question does not mention here at all finding the p's and q's and the rational zeros. So you don't need to do that unless the question specifically tells you to do so. So you could list all the p's and q's and find those p's over q's, but I'm not going to bother. Instead, what I'm going to do is I'm going to jump right in and try to find these zeros using my calculator as a guide, as sort of a helper to tell me where might be some good guesses. If you wanted to use the p over q's as a guide as well, you certainly could do that, but that's not required in the instructions of this particular problem. So I'm going to go to my y equals, clear out my polynomial, and I'm going to type in this cubic. So 7x to the third minus 32x squared plus 44x minus 16. And I'm going to hit graph. I'm still in that standard window. And we're not looking for the perfect graph here. This one actually does look pretty good in this window. We're really just looking for zeros. So where does this graph hit that x-axis? So I'm going to replicate this graph over here, and that's always a good idea when you're doing this on a test. Show the picture that you are referring to help you out. So I see a graph that looks like this. One tick mark is right there, and this right here looks like it's hitting right at 2. So I am guessing that 2 is probably a 0. What else can you notice about the graph and what's happening right at that 2? What kind of graphical shape do we see right at 2? Is this a 0 that passes right through and the graph continues to go right through 2? No. At 2, there's a bounce. And what does that mean if you have a bounce? If you have a bounce, that means you have to have even multiplicity. And that means that when we factor this cubic, if 2 really is a 0, and we will need to verify that, then it's going to have a square on that linear factor because we need even multiplicity. So it would need to be at least a 2. It could be a 4, but not in this case because we only have a cubic polynomial. So if it was a multiplicity of degree 4, then we would have to have at least a degree 4 polynomial, which we don't have. So I'm suspecting here that 2 is going to divide into this polynomial 2 times because it has multiplicity 2. So let's go ahead and verify that that's what happens. So we're going to take our coefficients of our original polynomial, 7, negative 32, 44, and negative 16, and I'm going to try and divide it through by 2. So bring down the 7 gives me 7, 14, negative 32 plus 14 is negative 18, 2 times negative 18 is negative 36, 44 minus 36 is 8, 2 times 8 is 16, and there's my first 0. So I know that that 2 is a 0 at least once. We think that it has a bounce going on there, so it should divide in again for that even multiplicity. So again, I'm just going to continue with my synthetic division using this quotient row as my new polynomial. So divide into what was left over. Don't start from scratch. So let's bring down our 7. 2 times 7 is 14. I'm going to get a negative 4, negative 8, and a 0. So we know that we have, for our 0, 2 with a multiplicity of 2. And what does this quotient represent in terms of its degree? We started with a cubic, so when we divide that by this 2, we're going to end up with a square here. And when we divide that quadratic by 2 again, this should be x to the first. So this quotient is linear, 7x minus 4. So where does that equal to 0? Well, that's easy to solve, right? Just add 4, divide by 7, so we get that x must be 4/7. So the other 0 must be 4/7. So my zeros are 2 and 4/7. Now that's only 2 zeros, but remember 2 had a multiplicity of 2, so it counts twice. So we've got 2 2's and a 4/7, so we've got 3 zeros total, which is going to agree with our degree 3 polynomial. Okay, let's try this again. So now we've got a 4th degree polynomial, and we want to find the exact value of all the zeros. So we're going to have to do this using synthetic division and maybe some solving, but we're going to use our calculator to help us give us a good guess for where to start. So let's go to our y equals, clear this out, and we're going to type in x to the 4th minus 6x to the 3rd plus 4x squared plus 15x, and then a plus 4. Make sure I typed it in right. Hit graph, and we're looking for zeros that hit right on those tick marks. So again, I'm going to kind of copy my graph over here for a reference, and it looks like it's doing something like this, sort of W shape. And the 0 on the leftmost 0, to me that looks like it's hitting at -1. The second 0, on my picture I have a bad graph here, but I have it showing that it's hitting at 0, but I think it's a little bit to the left of 0. And then this third 0 is hitting a little bit to the right of 3. And the 4th 0 looks like it's hitting right at 4. So to me, it looks like the only two that I can really have a good faith that they probably are actually hitting on integers would be at -1 and +4, and the other two look like they might be some decimals. So I'm going to use synthetic division using -1 and 4 as my guesses. So those are going to be my guesses for zeros. So I'm going to copy down my coefficients, 1, -6, 4, 15, and 4. And let's start with -1. Bring down my 1, 7, -7 is -3. Oh, sorry, this should be -7, so this is +7. I added wrong there. So we get an 11, -1 times 11 is -11. This is 4, -1 times 4 is -4, so there's my 0. So -1 did work. Now I think 4 works, so I'm going to use 4 in my little box on the quotient here. So I bring down my 1, 4 times 1 is 4, -7 and 4 is -3, 4 times -3 is -12, -1, -4, and there's my 0. So that also worked. So far I know for my zeros that I have -1 and 4, and there's probably 2 more here because we can see them and they must be either fractions or decimals. So I'm going to use the quotient that we ended up with here and try to solve that. We started with a 4th degree, so when I divide that once I get a cubic, and when I divide by that again I'm going to end up with a square. So this is an x squared and an x, so we're talking about x squared minus 3x minus 1. And that does not look like it's going to factor, so we're going to have to use the quadratic formula. So x equals minus b, which would be plus 3, plus or minus b squared, -3 squared is 9, minus 4 times a times c, which is -1, all over 2 times a, 2 times 1. So that gives me 3 plus or minus. A minus minus is going to become plus, so this is a 9 plus 4 under that radical. And that is going to give me 3 plus or minus square root of 13 all over 2. And the radical doesn't reduce here, and none of the outer numbers cancel out. So my 2 zeros are just 3 plus or minus root 13 all over 2. And you could write them separately if you wanted to. You could do the plus case, comma, the minus case, or just write them both together using that plus or minus symbol. And there's 4 answers right there, and this was degree 4, so I've gotten every 0 that I was supposed to get. Okay, let's try another one. Okay, so this time we have a 6th degree polynomial, so we could have as many as 6 different zeros. Not necessarily. Some of those may repeat, or some of them may be complex, so we won't be able to see them. So let's go ahead and jump to our graph here, and I'm going to have to be real careful typing this guy in because it's got so many terms. So be patient here. 2x to the 6th minus 3x to the 5th minus 13x to the 4th plus 29x to the 3rd minus 27x squared plus 32x minus 12. Let me double check. 2x to the 6th minus 3x to the 5th minus 13x to the 4th, 29x cubed, 27x squared, 32x minus 12. Let's hit graph. Okay, so you could zoom out on this if you wanted to a little bit, just to see the shape of that graph a little bit better. But to me, it's looking like we've got something going on like this, and it comes up, turns around again, and then does something like that. Okay? So right over here, this is hitting exactly at -3, it looks like to me. So I think I have a guess of a 0 at -3. This guy over here, it's hard to tell. It's sort of between 0 and 1. And then this one over here looks like it's hitting right at 2. And that is a bounce going on right there. So that means it's going to have even multiplicity. And since this is degree 6, that means it could be even multiplicity of 2, 4, probably not 6, right? Because we knew that we had another 0 over here. So it's probably a degree 2 or a multiplicity of degree 2 or 4. So let's see what's going to happen here. We're going to take our coefficients all the way across the top. So 2, -3, -13, 29, -27, 32, and -12. And let's go ahead and divide through by that -3 first. So I bring down my 2, I get a -6, so it's -9, 27, which is 14, -42, -13, 39, just 12, negative 36, just negative 4, positive 12, and a 0. So that one worked. Now let's try our 2 on this quotient. So I bring down my 2, I get a 4, just negative 5, negative 10, 4, 8, negative 5, negative 10, 2, 4, 0. And we know that it had even multiplicity, so it's got to go in at least one more time. So let's try again. 2 and 2 is 4, negative 1, negative 2, positive 2, 4, negative 1, negative 2, and 0. Okay, at this point, we started with the 6th degree, then we have 5th degree, then we have 4th degree. So this quotient down here would have to be 3rd degree. Okay, and unfortunately we don't have a nice formula like we do for the quadratic formula to solve cubics. So we're not quite low enough to be able to take over here and use either factoring or quadratic formula on this quotient because it's still cubic. So here is where we're going to have to make another guess. Either we think that this 2 might go in higher, and you could try. Let's go ahead and try. So bring down the 2. Here's 4, 3, 6, 8, and that's not going to work, right? So I'm going to scratch all that because 2 did not go in another time, which means its multiplicity then must be 2, since it only worked twice. So we're going to have to go back to our graph over here on our calculator, and we're going to have to make a good educated guess to see if we can try and get this cubic quotient that we have down here 1 degree lower so that we can take over and solve this algebraically. So let's look at our calculator graph one more time. We've already used the negative 3, and we've already used the 2 twice. What about this other 0 that I see over here? It looks like it's between 0 and 1, right about halfway. So if I might guess a half, is that a potential 0, a rational 0? Remember that rational 0 theorem that we did at the very beginning of the lecture today? We got those p's over q's. Is 1/2 going to be one of those p's over q's? Because if it is, then it might be a good guess that we could try on our synthetic division. So the p's would come from this 12, and the q's would come from this 2, and the factors of 12 would be 1, 2, 3, 4, 6, and 12, and the factors of 2 would be 1 and 2. Let me write those all out. So 1, 2, 3, 4, 6, and 12, plus or minus, and the q's would be factors of 2, which are 1 and 2. Can I get a 1/2 out of this? Yes, if I do this 1 for the p over this 2 for the q, then 1/2 is a potential rational 0. So what I'm just trying to remind you of is that rational 0 theorem, it can be used to help justify why you might guess that this is hitting right at 1/2. So let's try it and see if it really does work. You always have to check. You can't just assume it because of the calculator. You always have to verify it using synthetic division. So if we bring down our 2, 1/2 of 2 is 1, negative 1 plus 1 is 0, half of 0 is 0, 2 plus 0 is 2, half of 2 is 1, negative 1 and 1 is 0. So yes, it worked. And the even better news is if this is a 6th degree, this is a 5th degree, 4th degree, 3rd degree, this is squared. So that means we have 2x squared plus 2 as our quotient, and that is something we can solve algebraically. We don't even need quadratic formula. We can just get our x squared on one side by subtracting 2, divide by 2. Where does x squared equal negative 1? If I take a square root of both sides, I get x. Don't forget your plus or minus symbol. And what's the square root of negative 1 called? It's called I. So this is going to give us two imaginary or two complex solutions. So let's list out all the zeros that we got and make sure we got all of them. We had negative 3 from here. we had 2, which had a multiplicity of 2. That was here and here. We had a half from here, and then we had plus or minus I. So we have negative 3, which is 1, 2, 3, 4, 5, 6. 6 different zeros happening. And that's good because we had a 6th degree polynomial. So we must have found them all. And just to make a little quick note here, remember those conjugate pairs? I and minus I are conjugate pairs as well. So complex solutions will come in conjugates also. Okay, so on that last example, we had some complex solutions as well. We know that an nth degree polynomial, we said this earlier, can have at most n real zeros. In the complex number system, an nth degree polynomial has exactly n zeros, counting multiplicity. This is a very important theorem called the fundamental theorem of algebra. So whatever the degree of your polynomial is, you will have to have exactly that many solutions. Some of them may be real, some of them may be complex, and some of them may repeat. So what we're going to do is find all of our zeros, and then I'm also going to ask you to factor it completely. So let's take a look at x cubed minus 8, and we're going to try to find all the zeros, and we're going to try to factor it completely. So hopefully x cubed minus 8 looks a little bit familiar, because if you were going to be asked to factor this, you should recognize that this fits a pattern. It's called a difference of cubes, because we've got a cubic power and 8 is a nice perfect cube. And there's a formula for how to factor a difference of cubes and also a sum of cubes. So let's review how to do that. It has two factors. The first factor will have two terms in it. The first expression or term here is the cube root of whatever you see right here, so just an x by itself. And the second number over here is the cube root of 8, which is just a 2. And if this is minus here, then this first factor is minus. Then your second factor is actually going to be a trinomial. It'll have three terms, and you get that by taking this x and squaring it, this 2 and squaring it, and that's always positive. And then your middle term is these two multiplied together with the opposite sign of what you see right here. So if this is minus, this needs to be plus. And you need that opposite sign so that if you were to distribute this all out, all of those middle terms end up canceling each other out, and you just end up with the very first term and the very last term. So we've got it factored, but it's not considered factored completely because this quadratic over here has some zeros in it that we're going to need to figure out. I know that this is a 0 right here that I can easily see to be 2, but we also need to find the zeros from here. So since it's quadratic, let's just use our quadratic formula on it. It's not going to factor any further, and it never will when you have a difference of cubes formula. So this is not factorable, but we can do the quadratic formula on it to find out what its zeros are. So x equals minus b, so the opposite of this 2 would be minus 2, plus or minus b squared, which becomes a 4, minus 4 times a, which is 1, times c, which is 4, all over 2 times a. And this reduces to negative 2 plus or minus. We get 4 minus 16, which is a negative 12. That can reduce, okay, negative 12, whoops, square root of negative 12. First thing I'm going to do is pull out that I. Whenever you have a negative under your radical, that's going to be turning into a complex number. And then square root of 12 is square root of 4 times square root of 3. And square root of 4 turns into a 2. And just to make it a little nicer, I like to put my coefficient in front of my I. So this would be negative 2 plus or minus 2i root 3 all over 2. And finally, all of these outer coefficients are going to cancel out. If you divide them all by 2, you're left with negative 1 plus or minus I square root of 3, and the 2 on the bottom goes to a 1, and I don't need to write it. So what are my zeros? Let's find that out first. This factor gave us a 0 of 2. This factor gave us two zeros, -1 plus or minus I root 3. There's those complex conjugate pairs. So we got 3 different solutions because this was cubic. So we got all 3 of them. Now I want to factor this completely. So when it says to factor completely, you may think you're done when you get to here because this looks like it's prime and it doesn't factor any further. But we're going to allow complex or imaginary zeros here. So we are going to allow this to be factorable using these zeros as their roots. So we know that one of the factors is obviously x minus 2. The other 2 factors have to come from these other 2 zeros. And just as kind of a side note for a moment to help you see and understand where this is coming from, suppose that we wanted a solution of -3 and +6. I'm just making up 2 numbers. What would the factors have to be to give you a 0 of -3? The factor would have to be x plus 3, right? And what would the factor have to be to give you a solution of +6? Would have to be x minus 6. So that's what we're going to do on these 2 zeros right here. If I want to get a 0 of -1 plus I root 3, then my factor would have to be x minus that whole 0. And I'm going to wrap it in parentheses. So it would have to be x minus that whole quantity, -1 plus I root 3. Similarly, if I want to get the minus case, then my factor would have to be x minus the minus case, -1 minus I root 3. It's always going to be x minus, and then if you have these complicated zeros like this one is because it's complex, just wrap it in parentheses, but it's always x minus whatever that 0 happens to be. Now if you want to, you can distribute this negative across both of these parentheses, and this would become x minus 2 parentheses x plus 1 minus I root 3, and this would become x plus 1 plus I root 3. And that is what we mean when we say factored completely in the complex number system. So we're allowing you to have i's in your factorization, and to be factored completely, every factor should be linear, so an x to the first power, and it should have no coefficient in front of that x. Alright, let's try another example. Find all the zeros of x to the 4th plus 10x squared plus 25 and factor it completely. So what I like to do on these factoring problems is I always try to factor this as much as I can first using any of the factoring strategies that we already know, and then if I can't factor it any further like I'm used to, then that's when I break down and bring out my algebra. So for example, x to the 4th plus 10x squared plus 25. Does that factor? Well, it's a trinomial, so potentially it could have 2 factors like this. If I put an x squared and an x squared here, that would multiply to an x to the 4th, and it will also give me that x squared that I need for the middle term. If I put a 5 here and a 5 here, that'll multiply to 25, and in the middle it'll give me that 10x squared that I want. And I need these both to be plus for that to happen. So yes, it does factor. But this is not considered factored completely because these are quadratic factors. So since I can't really factor this any further using any of my patterns, it's not really a sum of cubes or a difference of squares or something like that, here's where you bring out your algebra. So if I wanted to know what the zeros of this factor were, I would set it to 0, subtract that 5 over, take a square root of both sides, don't forget your plus or minus symbol. There is a negative under that radical which is going to pull out into an I, and then square root of 5 is reduced already. So this factor has as its solution 2 complex numbers, plus or minus I root 5. this factor also has those same two solutions. So my zeros are just plus or minus I root 5. I get both of those from this and both of those from this. So they both occur twice. They each have a multiplicity of 2. And that's why I have a degree 4 here, because each one's counting twice. So that would be a total of 4 zeros. So those are my zeros. And now let's factor it completely. So to do that, let's take the plus case first, I root 5. If that's one of my zeros, then what factor would it have to have in the factorization? It would have to be x minus that 0, so x minus root 5. Okay? If I wanted the minus case, minus I root 5, then what factor would I have to guarantee that? I would have to have x minus a negative I root 5, which becomes x plus I root 5. So these two, if I were to FOIL them out, you would end up getting back x squared plus 5. But remember, they each had a multiplicity of 2, so far I've only got 2 factors. I should be having 4 since this was a degree 4 polynomial. And since they have a multiplicity of 2, that means I want to use this one twice and use this one twice. So we just put some little squares on the outside. Inside it's still a linear factor, which means it's factored completely. It's just the multiplicity is going to be that power on the outside. So here we've done it. We've found our 2 zeros and we've factored it completely. Okay, here we go again. So this time we've got x cubed minus x squared plus x. So I'm going to start by trying to factor this as much as I possibly can. And it's cubic, and we don't normally know how to factor cubics very well, but this one we get a little bit lucky because all 3 of these terms have an x in common. So I can pull out an x like a GCF, and that will leave me with an x squared minus an x plus a 1. Now does this quadratic here factor any further? It doesn't look like it. There's no way that I can multiply to a 1 on the end here and still have a middle term of negative 1. So to me, it looks like we're going to have to break out the quadratic formula to find the zeros of this quadratic. So that would be x equals minus b, which becomes plus 1, plus or minus square root of b squared, negative 1 squared is 1, minus 4 times a times c, all over 2 times a. So that's going to give me 1 plus or minus square root of 1 minus 4 is negative 3. And if I pull out that negative and turn it into an I, then I get 1 plus or minus I root 3 all over 2. So there's 2 of my zeros. 1 plus I root 3 over 2, and 1 minus I root 3 over 2. Or you could just list it as 1 plus or minus I root 3 over 2. You can list them separately or together with that plus or minus symbol. Either way is fine. Now this was a degree 3, so here's 2 zeros. Where's my third one? Don't forget this guy. Remember that x that we pulled out way from the beginning? When does that factor equal to 0? That factor equals 0 when x is 0. So our third 0 is right at 0. Now let's factor it completely by converting these into our linear factors. To get the 0, you just need that x factor. To get 1 plus I root 3 over 2, we would need x minus this whole quantity. Use parentheses here. And to get the other case, the minus case, we would need x minus that entire quantity. So again, I'm always doing x minus stuff, and then just changing the stuff depending on which case I'm using. If you want, you can distribute your negative across, so this could be x minus. You can even split this up if you want. Just a little note here that 1 plus I root 3 over 2 is the same as a 1/2 plus I root 3 over 2. So if I were to distribute that negative, this is just an option, you don't have to do this, but if I were to distribute this negative across, you could see this written as x minus a half minus I root 3 over 2. And this one would be x minus a half as well, but the minus minus would become plus I root 3 over 2. So that's just another way to write it as two separate fractions, if you want to. Okay, let's try another one. 3x to the fifth plus 24x cubed plus 48x, factor it completely. So I'm going to start with this fifth degree polynomial, and I'm going to try to factor it as much as I can first and then pull out the algebra when I need to. So if I look at this, it's a fifth degree, but it looks like I've got an x in common throughout, and I also have a factor of 3. 3 goes into 24 and 48 as well. So I have a GCF of 3x. If I pull that out, I'm going to be left with an x to the fourth plus an 8x squared plus a 16. Now this fourth degree that we're left with here, does it factor any further? And it looks like it has good potential because this middle term is half the degree of the leading term, so potentially this could factor like a trinomial where I have an x squared and an x squared to give me that x to the fourth. It'll also give me the x squared in the middle, and if I put a 4 times 4, that'll give me 16, and a 4 plus 4 will give me the 8. So it does seem to work, so this looks good. Now each of these, they're close to being a difference of squares, but they're sums. So I can't use that difference of squares pattern on these because of the wrong sign, which implies that these are probably going to be complex solutions. So let's go ahead and solve them algebraically. Set this equal to 0, subtract 4, and take a square root of both sides. I'm going to get an x, I'm going to get a plus or minus, the negative becomes an I, and square root of 4 becomes a 2. And this is going to give me exactly the same thing. Don't forget this GCF. When does 3x equal to 0? When x is 0. So I have the following zeros. I have 0, and I have plus or minus 2i. And each of these have a multiplicity of 2 because I had them occurring twice. So these count twice each, so that's 4, plus the 0 makes 5. So I have my degree 5 covered. Let's factor it. To get the 0 factor, we need just an x. To get the plus 2i 0, I would need x minus 2i, and it occurs twice because of that multiplicity. And to get the minus 2i case, I would need x plus 2i, and again it had multiplicity 2, so I want to count it twice. So I've got degree 1 plus 2 more makes that degree 5. Okay, last page here. Find all the zeros of this fifth degree and factor it completely. So let's go ahead and see what we've got. This is a big fifth degree, and it doesn't have a GCF like the last example did. So trying to factor this right from the start is probably not going to lead you very far. So what we're going to have to do is probably break out the calculator to help us get a feel for what some of these zeros must be. So I'm going to go to my y equals, clear this out, and I'm going to type in x to the fifth minus x to the fourth minus 4x cubed plus 8x squared minus 32x plus 48. Make sure I got it right. Hit graph. And my graph is looking something like this. Right here, it looks like it's hitting at -3. And right here, it's looking like it's bouncing at 2. So the 2 being a bounce means it's going to have even multiplicity, maybe it's occurring twice. The negative 3 would occur once, so that's 3 times. So either this multiplicity would be all the way up to 4, so we would get our degree 5, or else the other 2 zeros that I'm not accounting for here might be complex. Okay, so we're going to use our synthetic division to verify that these really are zeros. So let's put our coefficients across the top. And I'm just going to start with that 2. And we would get 1 here, 2, 1, 2, negative 2, negative 4, 4, 8, negative 24, negative 48, and there's our 0. We know that it has an even multiplicity, so it's got to go in again, so let's try it again. 1, 2, 3, 6, 4, 8, 12, 24, 0. So that looks good. Let's try our negative 3 next. So I have 1, negative 3, 0, 0, 4, negative 12, 0. Now, this was a 5th degree, so this quotient is 4th degree. This is cubic, so this is squared. So my quotient here is x squared plus 4. So if I set that to 0 and solve, then we will get our last 2 solutions. Take a square root of both sides. You're going to get plus or minus. The negative becomes an I, and square root of 4 is 2. So our zeros are going to be plus or minus 2i, 2 with a multiplicity of 2, and negative 3. And then how does all of this factor? Well, to get the factor of negative 3, I would need x plus 3. To get the factor of 2, or the 0 of 2, I would need x minus 2. And since it had a multiplicity of 2, I need a square on the outside. To get the 0 of plus 2i, I would need x minus 2i. And to get minus 2i, I need an x plus 2i. So we've got degree 1, 2, 3, 4, 5. There's our 5th degree. And we've got our answer. Okay? Last example. So here's our 4th degree polynomial. Again, it's pretty messy and it looks fairly difficult to factor, so I'm going to jump right in with my graph and try to get a guess going on here. So 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18. And if I hit graph, we don't see a whole lot on our graph, but it looks like I've got a 0 over here at negative 2. So it's looking something like that. So my guess here would probably be that 0, one of the zeros is at negative 2, potentially. So let's do our synthetic division. 3, 5, 25, 45, and negative 18. And I'm going to guess that negative 2 goes into that. So I would get 3, negative 6, negative 1, 2, 27, negative 54, negative 9, positive 18, and there's my 0. Now, it's very difficult to see what this other 0 would be. It doesn't even look like it's hitting right at halfway. So what we're going to have to hope is that this quotient that we're left with is something that we can deal with algebraically. Since we started with a 4th degree, it's got to be 1 degree less, so this has got to be cubic. 3x cubed minus an x squared plus a 27x minus a 9. And it is cubic, which means usually we don't really have a whole lot of success with factoring cubics. There's no common GCF going on here, but if you remember one of your factoring strategies, this has 4 terms, and it has good potential for being factorable using the grouping method. So if I group these 2 together and these 2 together, we might be able to pull out a GCF from each of those pairs. So these 2 I can pull out an x squared, and I would be left with a 3x minus a 1. And then if I go to these 2, they both have a 9 in common, so if I pull out a 9, I would be left with 3x minus 1 as well, which is really good news because now these 2 factors match. So I can pull out a 3x minus 1 in parentheses and be left with the x squared plus the 9. And that's excellent because this then has a solution of positive 1/3, which is probably this guy over here, and this would have as its solution, if I subtract the 9, take a square root, plus or minus, the minus becomes an I, and the square root of 9 is 3. So my zeros are going to be plus or minus 3i, 1/3, and don't forget that negative 2 that we started with. And there's 1, 2, 3, 4, and this was a degree 4 polynomial, so we have all 4 zeros that we were looking for. Let's factor it, and then we're all done. In order to get the 0 of negative 2, I would need x plus 2. In order to get the factor of that 1/3, you can have x minus 1/3. Actually, I'm going to back up here and take that away. Remember over here we had 3x minus 1 as our factor? That's where it came from, 3x minus 1. And in order to get the plus or minus 3i, we would just need x plus 3i for the minus case and x minus 3i for the plus case. Now that is considered factored, but it wouldn't necessarily be considered factored completely because this factor right here doesn't have a coefficient of 1 in front of that x. And sometimes books and textbooks can be picky about that. So if you think about 3x minus 1, how could you make it have a coefficient of 1 in front of that x? You could pull out the 3 and be left with that x minus 1/3 that I hinted at earlier. If I do that and rewrite this, this is 3 parentheses x minus 1/3, and then these other factors we had were x plus 2, x plus 3i, and x minus 3i. Now if I didn't have that 3 in there, I wouldn't get this to match the original polynomial that I started with because this original polynomial had a coefficient of 3x to the 4th. So if I had left off that 3, then it wouldn't quite match. It would have the same zeros, but it wouldn't be the exact same polynomial. So it's always best to go back to some of those factors that you got algebraically and then pull out any coefficients as coefficients in front of the whole thing. That way your final factorization matches the original polynomial. Alright, that concludes our lecture on the zeros of a polynomial. Good luck.